My name is Georgia. I've been working at Facebook AI Research for the last 5 years, but I've been working on visual recognition and computer vision way more than that. And that's what I'm going to be talking to you today about some of the really exciting work in computer vision, visual recognition that I've had the luck to work on for the last years. And just to give a brief description of what visual recognition means, I want to show you this image that you see on my slides. What you see here is a typical image, an image of a scene with a lot of people, objects. There's a lot going on. So what every researcher working in this field of visual recognition hopes is to build a system that can understand exactly the things that we humans see when we look at this image. We want to recognize all the objects. We want to recognize all the people. We want to parse people's pose. We want to understand how the people interact with each other and the objects. And we also want to get more information about these objects, for example, their 3D shape or their pose in the scene. So basically everything that one can hope to understand from this image. And it's been really fortunate that the community has actually built and established benchmarks that separate this big problem of understanding everything into understanding simpler things. So separating into smaller subtasks. And usually these benchmarks consist of thousands of images. They're quite complex and allow us researchers to evaluate quantitatively how much progress we're making towards these tasks. And today I'll be talking about a lot of these tasks. I'll be talking about instance segmentation, which is a task that aims to understand objects and recognize them in the image. I'll be talking about human pose estimation, about understanding human-object interactions, video tracking, and last about understanding objects in 3D. And just to give you a little preview of where we are in the field, I'm showing you here the output of a library that I, along with more collaborators, have open source. It's called Detectron and hosts a variety of state-of-the-art recognition models that take in an input image and are able to understand and predict all of the things that I just talked about in this image. And Detectron 2 is, Detectron 2 is a set of 2 libraries, is something that has allowed the field, along with the benchmarks, to actually progress. It allows users from all over the world to download the library, download the models, and start from a state-of-the-art working system and extend it to do even more and greater things. So onto the task of 2D object understanding. The task is as follows. You're given a 2D image as an input, and this image is a real-world image of any complex scene. It has a varying number of objects under occlusion, clutter, any lighting conditions that we do not control, of course. And the goal is to predict all the objects. And what I mean predict here is, it means that you need to predict a 2D bounding box that encloses the object. You need to predict an object label. So for example, it's a bookcase or a sofa or a chair. And also you want to predict the 2D silhouette of that object. And a lot of the things that I'll be talking about today, especially in the first part of the talk, will be supervised. So we're going to be using annotations that exist on the training set to supervise a model to perform this task. At test time, of course, we don't assume any ground truth knowledge, and it's just a mere inference from the image input. And in particular, we'll be talking about MaskCnn, which is a work that's from 2017, but is the basis of a lot of the recognition work that we do until today. So MaskCnn is a neural network. It's a deep net that consists of 2 parts. The first part will take an input image and will process it with a CNN. We usually call this a backbone network, which embeds this input image into a higher dimensional feature space. And this network and this process is actually shown with like a flattened rectangle here, but it's actually the topic of very exciting research work till today of how to design these great and deep CNNs that are able to extract the necessary information from the image that we need for recognition. And usually we use ResNets. ResNets are these humongous neural networks consisting of hundreds of layers, convolutions, nonlinearities, stacked one after each other. But this community is actively changing, and we see a lot more exciting work happening. But for the purpose of this work, any CNN would work. Of course, the better the network, this backbone CNN is, the better luck we have at performing better for this task. So this image level operations from the backbone CNN are then followed by region-wise segmentations. So this region-wise operations happen at all the candidate objects that we have detected in the image coming from the previous image level operations. But we've now focused on every region independently. So we want to analyze every object, and we do so by feeding these extracted regional features through another smaller network that's usually designed and tailored for the task that we want to solve. In this case, we want to solve for instance segmentation, meaning that we want to be able to mark the silhouette of the object. So we're going to use convolutions in order to achieve that. Later on in the talk, I'll show how you can design these operators to be for different types of tasks. And of course, we need to have a component that glues these two stages, the image level operations and the region-wise operations together. And that is this operation that we call ROI Align, which is a seemingly very simple operation. All it does is extracts the features that correspond to a region that we have identified as being an object candidate, from the bigger feature map that our backbone CNN has output. And it turns out that you actually need to be a little bit careful when you are designing this ROI Align operator that extracts features. And in particular, you want to make sure that you maintain the equivariant properties of your network when you do this, which means that you want to make sure that you are obeying the coordinates of the regions without doing any cropping or quantizing of the ROIs. And this is what we were doing before in the community. We were not being very careful in how we were extracting these features. And it turned out that by just doing this very simple fix of maintaining this equivariant properties allowed the networks to perform much better. And here I'm showing you exactly what a network like MaskCnn outputs, where I'm showing you a bunch of images from the test set, images that the network has never seen before, and the predictions from MaskCnn. And again, there is no real ground truth information here whatsoever, so the network has to detect all the objects and mark the silhouettes. And this was at the time something that we were extremely excited about, especially you look at this image on your the third column, second row, where I don't even know what's going on in that image as a human. Like there's so many things going on, and you see the network being able to meticulously detect every single object and the silhouettes. And it turns out that it's not just instance segmentation that this model can tackle. With a very simple change in the region-wide computations, we can also go for human pose estimation. Human pose estimation is the task of predicting for every detected human instance in the image, localizing the various key points of the human. For example, the right shoulder, or the right ankle, or the right eye, the nose, etc. And with the same strategy and the same ideas, we can achieve this with a model like MaskCnn. And here I'm showing you exactly one again, some predictions on images from the test set. And And as I said, detecting objects and recognizing objects is definitely one part of what we want to solve of this bigger idea of understanding everything from an image, but there is a lot more other tasks. Especially interesting is a task of human-object interactions, where here what we want to predict is we want to detect, again, starting from a single image, we want to detect all the humans in the image, but also understand what activity they're performing and also with what objects they're interacting while they're performing that activity. And I'm showing you some examples here of human-object interactions, as we call it in the community, where we see the human being detected, a verb, which is the activity that the human is performing, and another object, which is the object of interaction while performing that action. And of course, once again, we're going to work and base our model on the same principles as MaskCnn. So we will have an image that's being fed into a CNN, a backbone CNN, and then we're going to have regional features being extracted from the object, the candidates for the objects, and we're going to process them. And we're going to process them in ways that are tailored for the task at hand. So this model that we call InteractNet and that we have developed for this task incorporates MaskCnn because we need an object detector. We need a way to detect all the objects in the image. But it does more than that, as it has to focus on the humans that are being detected in the image. And for each detected human instance, we want to predict their action. And we also want to, so that's the verb. And we also want to predict a location, a possible location of where the object of interaction would be purely based on the appearance of the human. So without seeing the object necessarily, what is a good guess of where the object of interaction is? And I'm showing you what these predictions look like, this intermediate predictions from the network on this image on the bottom right with a red heat map. So you see that, for example, the guy that's throwing something on the far right image, we predict that there is possibly an object somewhere in front of him, which is denoted with this red heat map. And this is exactly done purely from the pose of the person. And finally, we want a third branch is which will condition not just on the pose of the human, the appearance of the human, but it will take in the objects as are detected from our detection brands. We'll try to score these pairs of human and objects for particular actions. So at inference time, the predictions coming from the second branch, the human-centric branch, and the third branch, the interaction branch, will come together. It will make a hypothesis about what is a potential triplet of human, verb, and object for an interaction. And I don't really want to bore you too much with numbers here. That is not really the goal of this presentation, but I wanted to say that all of these networks, all of these three branches that I presented are actually very important for the final performance. So, and this usually is something that drives how we design models when we want to tackle these tasks, where we want to be carefully evaluate how important every part is of the network. And it turns out, of course, that through our qualitative analysis, that the most important part of the network is that second branch that tries to give an estimate of where the object is, because that allows the model to anchor more accurately in the potential object of interaction.
Georgia, quick question from the chat room. When you say that the target position is calculated only on the person pose, do you mean that it's on a crop of the image of the person or on the pose estimation only?
Yeah, no, that's a great question. So I think that the right way to do this is the appearance. So it is on, it's not on it's basically on these ROI extracted features on the human. So the only thing that the network see is the appearance of the human. that is detected. So the network doesn't have access to the objects necessarily at that stage. We're not using the pose. Actually, we try to also use the pose at some later works, but it turns out that the pose is already incorporated into these features. The pose is actually a cue that the networks use for this task. Okay. And I don't have these images to show here, but by looking at the errors that the network does, you see the pose is one of the most salient characteristics that it latches on when it wants to make these predictions.
Thank you.
Yeah.
Hi, I'm Jiayang Liu. I'm a grad student in Gkioxari. I have another question. How do you determine a region is of interest?
Yeah, so this happens. I didn't really cover it because there's so many things to cover, but this happens through another little network that we usually train off of. I don't know if you can see my screen, but just after the backbone CNN operates on the image, we have this network that we call region proposal network that tries to predict possible candidate regions in the form of boxes for the image.
I see. Thank you.
And this at that stage, this is also I want to say it's class agnostic, so we'll just say object or not. And these are the candidates that we go with.
I see.
And that we then also clean up in a way with our more sophisticated networks.
I see. Thank you.
Yep, of course, great question. And you know, if we're in this sort of, I've been presenting a lot of tasks, so I'm going to present one more. And these are actually all very related because they are extensions of very similar ideas that have had a very big impact in this world of visual recognition, and that is tracking from videos. So all of the work that I've presented so far in this talk have been using as input images. But we have been ignoring videos, and actually videos constitute probably the majority of the data on the web right now. And processing videos, of course, is also a lot more difficult because now you're seeing a sequence of frames rather than a single input. But we ought to develop models that operate on videos because this added dimension of time that videos have is very important to not only perfect visual recognition, but also be able to make do more from purely visual data. And doing more, tracking is one such representation, like it's one such task where the goal here is to be given a sequence of frame and you want to track all the humans on the frame. So track means that the same person that starts in the frame one, you want to follow that same person all the way to the end of the video. And once again, we're going to build on similar ideas like MaskCnn, where now everything that was happening before on 2D regions or 2D predictions now has an added dimension, the one of time. So region now become tubes, and predictions now become poses or any sort of representation, the way that you want to predict objects, but with an added time dimension. And of course, that means that now our networks are heavier, our operators are no longer operating in 2D. We now have, for example, 3D convolutions instead of 2D convolutions. We need to make predictions in a lot more, like our regions are actually also more dense because they need to cover both space and time, and our predictions also cover space and time. But what's the only thing that I would like for you to keep from all these sort of methods is that similar ideas being extended to approach these tasks are the ones that are currently working in visual recognition. That's great for us because that allows us to think more and develop these models and hope that we can actually tackle a lot of tasks with the same principles.
Georgia?
Yeah.
Just a question about this particular problem. Is there any work currently, like before the deep learning revolution, some of the best models for this incorporated a sense of dynamics, right? The tracking enhanced by the, you know you're tracking a physical thing, it's going to move according to sort of physical principles.
Correct.
Is there still work on that? Is that something that can help, or is it too hard to integrate? Like, it was easier then because the math was simpler.
Right. Yeah, that's a great question. So I'm not gonna lie. I think that I think that the work that I am, so actually depends on what you want to do. I feel that this goes the same for also dynamics or optical flow, like these things that are low level like cues that we have been using in the past. I was also very lucky to be working on computer vision before the deep learning revolution. So I have an insight into these things. But it turns out that a lot of the times these things are not incorporated into the networks, either because the network is able to extract the things that it needs from purely processing these images. So I want to say that incorporating explicit dynamics is not something that we've seen have impact in such models, but we also might not be working with the right benchmarks and have the right tasks to see dynamics work and influence the performance in a positive way.
Okay. Thank you.
But I am all in favor of using it. I think that we should be incorporating physics and not just be purely data driven, but have some sort of priors of how objects move. And I think that will come as we are especially moving towards more robotic driven tasks, I would say.
Thank you.
Cool. And so for the rest of this talk, I wanted to focus more. So we've talked about single images, we've talked about predicting images in 2D space, we've talked about processing videos, but still making predictions in 2D space plus time. So I wanted now to add another dimension to this problem, which is the dimension of 3D, like the fact that objects in the world actually that we live in is not 2D, but it's 3D. So objects have 3D shapes, humans have 3D shapes, objects have 3D properties. And so we want to be able to do exactly the same as we did for our 2D visual recognition, where we take an image input and we detect all the objects in the image. But we want to do this and also be able to predict the actual properties of these objects in 3D. And driven by our passion to improve visual recognition more and more, we try to tackle this task with a model that we call MeshRCNN. And I apologize for the similarity in the names. It's all M something RCNN, but it's a really great description because it really builds on the previous work MaskCnn, where you have an input image and you detect the 2D objects in that image. But MeshRCNN does even more than that because it is also able to recognize and predict the 3D shapes of these objects that we detect. And the representation of 3D, I know it's a big sort of topic out there, and there is no consensus of what's a good representation, but we believe that the meshes are the most favorable representation of them all, because they work very well with graphics engines, and they're really nice to handle, manipulate texture, and so forth. And so for all of you that don't know 3D, what meshes are, they're basically triangles that live in 3D space that are connected, and by connecting them, you're able to represent an object in any shape. And I want to say that you all see meshes all the time. When you see movies, all the visuals, like computer games, they all have some sort of mesh representation in the back that's being rendered to you. And while 3D meshes are great because they're really nice to manipulate and visualize, they are not very flexible when it comes to incorporating or predicting topologies, especially complex topologies. And objects have complex topologies. They can have holes, they can have convexities, concavities, they can be very complicated. And while meshes are fantastic, they're not able to capture them really easily, and especially in a differentiable manner. And this is why we choose to go through an intermediate 3D representation that is not the desired representation for our output, but is fantastic to capture topologies in this intermediate stage of the network. This is the voxels, which allow us to turn them on and off and thus allows us to capture topologies, holes, and etc. And then we morph voxels into meshes to get the final shapes. And the network that we use for this, once again, builds on our visual recognition state-of-the-art models like MaskCnn, which takes as input image and detects all the objects in the image. So in addition to detecting the objects in 2D, we want to detect the objects in 3D. So we added this voxel branch whose goal is to predict the shape of the object in voxel space. So it's a voxelized representation, which, as you can see in this figure, allows us to capture holes like the back of a chair. But as you can also see in this picture, it is such a clunky, chunky representation of the shape. So it's not really appropriate when you want to do downstream tasks such as manipulation or texturing or anything else for that matter. So while it offers us topology, it doesn't offer us anything more actually. So what we do is that we convert this voxel representation into a mesh and then further refine it. And this refinement is implemented through a sequence of operators. First, we have the operator ROI Align, which what it does is very similar to ROI Align that I described before. It tries to very accurately pull features for every vertex, so every point of the mesh in 3D space, project it back to the image accurately, and pull the features from the corresponding location. So now we basically have a 3D graph, a graph in 3D space, and every node of that graph has associated features with it. So 2D convolutions, which is a very popular operation for computer vision, is no longer relevant. So we're going to replace that with graph convolutions, so convolutions which operate on any graph in 3D space. And through a sequence of graph convolutions, we're going to finally refine our mesh by predicting how to deform the nodes, the vertices on the graph. And of course, you can do this in many stages in order to get to the desired output. And just to give you a little bit of insight of the importance of having this intermediate voxelized representation to capture topologies, I wanted to show you a few examples of 3D reconstruction networks which don't try to account for this topology, this problem of topology. So I'm showing you some image inputs on the top row, and also another approach called pixel to mesh, which that is similar to how we operate on meshes, but it only deforms an initial sphere in order to capture the final shape of the object. That means that the model doesn't really have the capacity to change the topology. It just has to be homeomorphic to the initial shape that it's using, in this case, a sphere. And the bottom row is our predictions. And as you can see, when you're not given the network the chance to account for topology, it will try to cover these holes of the objects that are very obviously there by actually it can't capture them. So it will try to stretch the vertices of the sphere out, but the graph still covers them with faces. So you have this effect of seeing these holes be covered by faces of the mesh, which is not fantastic. Well, a hybrid approach that uses a voxelized representation is able to more accurately capture holes.
This is Luca. I have one question.
Yeah.
Actually, about this prediction of meshes. So for once, I'm unclear if this is doing anything different than. So what do you think about this solution that you have a CNN that predicts the depth of a pixel?
Mm-hmm.
Would that be?
Yeah, I mean, so you're talking about, so predicting the depth of every pixel will definitely, so of course, if you, let's say that you can train a network that can do this, the problem is that there is parts of the objects that are never visible. For example, the back of a couch, let's say, that you have in an image, that will never be a pixel that you will account for and that is there in the image. So you need to cover the self-occluded parts of the objects. So, and a depth prediction network will never get to that.
How does this network that you propose predict the back of a couch when it never has the image of the back of a couch?
Because it's a supervised, first of all, it's a supervised method. So you supervise it with that shape, but it's able to extract when it sees a couch. It is able to get the fact that, couches will have this shape. So these are priors that the model gets to learn via learning, and then is able to predict them even though it can't see them from the input image, either at train or test time.
Okay, and just one quick more question. Can you explain again why you said that 3D convolution are not suitable for the refinement part and you have to use instead graph convolution?
Yeah, because you're no longer operating, so the space that you're now operating, which is the meshes, they no longer are on a map. They're no longer on a 3D grid. It's a graph where the vertices can be anywhere in 3D space, and you have connectivity between the graphs. So 3D convolutions and 2D convolutions are great when you have a 2D grid where connectivity is defined from neighboring pixel spaces or voxel spaces. But graphs, the connectivity is defined by the connectivity of the graph, the edge, and the vertices don't have to be close to each other in order to be connected. And they don't belong in a defined grid, which is something that 3D convolutions and 2D convolutions need. Does that make sense? Yeah.
Yep.
And then a quick question from the chat on this. This is from just images. There's no parallax, right?
No, this is from images, but I'll get to something else in a moment.
Okay, thank you.
Yeah. And of course, we also want to do this, as I said, the motivation for all this work is to be able to do this in complex scenes with a ton of objects. So we want to be able to recognize objects. There's 2D silhouettes and their 3D shapes all together. And I want to say that this is definitely one of the hardest problems I've worked in my lifetime so far. And it's very difficult for many, many reasons. One is the fact that it's hard to get a lot of annotations for this task in order to supervise your model at train time, because getting these 3D shapes annotations is not very easy. But there is definitely something extremely hard about finding the right space to do predictions, understanding the objects, the occlusions, everything. All of the shortcomings of our 2D recognition networks now are emphasized in this particular aspect of recognition in 3D understanding. And especially I wanted to say that there is other challenges other than the problem being, difficult conceptually. There is also challenges from the engineering point of view, where, let's say in this model, in this MaskCnn that I just described, a big part of the network, and also based on the question from the audience, operates on these very complicated data structures that have nothing to do with 2D grids or 3D grids that we are so familiar with using in deep nets. And these 3D operators that we need to have in order to process our data are extremely difficult to implement, and especially implement efficiently. So for example, there is, I didn't cover how exactly we train MaskCnn, what our losses are, but we have a particular 3D operator, which is a chamfer distance, which computes the distance of 2 point clouds. It's a very popular, well-known metric that is being used in 3D object recognition and 3D understanding. But it turns out that if you try to implement this 3D operator, this chamfer distance, naively in PyTorch, which is a very commonly used deep learning library, you'll see that it's so slow that training would actually take weeks. So you really need to make it faster, and that will happen by going in and writing your own custom implementation for this particular operator. And so in this, along with many more operators and many more needs that 3D object understanding has, led to this really great effort that I was very happy to work in called PyTorch 3D, which is a library which is meant to be used for 3D object understanding. So this works in tandem with PyTorch and allows you to train deep nets end-to-end very fast using these complicated operators. And one feature that I'm very proud of that we have in PyTorch 3D, which has led to us being able to think more and do more in the goal of understanding everything from images is this notion of differentiable rendering. And I don't know, I'm sure a lot of you have heard of traditional rendering, which takes a 3D shape, a texture, and a camera, and renders it from that camera's view into a 2D image. Now, differentiable rendering tries to make all of this operators differentiable that allow you to go back from the rendered RGB image all the way to the shape, the texture, and the camera. And so that allows you to update all of these parameters while incorporating into a loss while training. And I want to cover a little bit about the idea that we had behind how to go about making rendering differentiable. And first, I want to spend a couple of minutes sort of giving you a brief explanation of why rendering is naturally not differentiable. So in traditional rendering, it consists of two steps. There is rasterization, which basically checks which primitives in the 3D world hit which part of the image. And then there is shading, which computes the color of each pixel after you've done rasterization. Now, shading is differentiable naturally, so it's just an interpolation of vertex data, so there's nothing really difficult there. All of the source of all of our headaches is this step of rasterization, which is not differentiable because of the boundary and the occlusion issues. And just to explain that a little bit more, focus on the green pixel on this 2D grid that you see. I hope you can all see it. It's right here. I don't know if you can see my mouse, but this green pixel. And look at the blue triangle in this 3D world that's being projected on the 2D image. And what happens when I take the blue triangle, put it all the way on the left, and slowly move it towards right? So initially, this green pixel will only contain parts of the orange triangle, but then as the blue triangle comes and covers it, it will switch color to be blue and then back to orange. And that leads to this step, which is not differentiable because of this boundary issue. That is exactly what makes us not be able to take any gradients. And in addition to XY discontinuity, we also have a Z discontinuity. Again, look at the green pixel and consider what happens to it when I take the blue triangle and move it from close to far. So the green pixel will start off being blue because the blue triangle is in front of it. But as I move it further away, the orange triangle goes in front, and the green pixel turns into orange. So again, we have the step function, which is not our enemy for differentiation. So the idea behind making rendering differentiable is to basically to smooth these boundaries and converting these steps into ramps. And that is what, and that essentially means that what happens is that we're blurring the 3D world in a way in both Z and also XY. And maybe I don't have a lot of time to maybe cover the differences between other differentiable renderers, so I will try to sort of skip that unless there is a question from the audience. But basically what this now allows us and what our implementation allows us in comparison to other implementations is that we can now have a very modular differentiable renderer where every component of rendering, including camera transforms, rasterization, and shading, are now separated into different operators compared to just being like a huge CUDA kernel written in a very complicated manner. So users are now able to tune all of these aspects of rendering based on the needs of their project. They can tune rasterization, they can tune shading, which is something that PyTorch has been able to do and has proven very useful for a lot of projects that I will try to present very fast in the next few minutes. And in particular, what differentiable rendering has allowed us to do has allowed us to think a little bit more about the problem of 3D object understanding without potentially requiring 3D annotations, which is, as I said before, one of the biggest bottlenecks in making 3D object understanding be extremely solid and effective for visual understanding. And in particular, you can now think of understanding objects in 3D by, instead of using 3D ground truth, instead you use multiple views of these of objects. So, for example, this is a little project that I worked on with a UC Berkeley student, Shubham, and the problem here was as follows. So we want to have input images of an object. These images you see on the far left. And we want, starting from these input images, we want to be able to extract the 3D shape and texture of the object without having any 3D ground truth. So we're going to do this by using this idea of differentiable rendering, which allows us to propagate information back from 2D images to 3D shapes. And through this idea of extracting 3D shape from differentiable rendering, we're able to do things like what I show in this image, where we have a bunch of images of the statue of a horse, and now we can extract its 3D shape and also texture it based on what we see in the input images. And the idea here is actually pretty simple. It follows from the idea of traditional model-based stereopsis that is a popular idea that allows you to reconstruct 3D scenes and from 1996, but we're going to do this with modern tools of differentiable rendering. And all the idea behind this is that you have a shape estimate, you warp it under camera view, and then you compare it to your views. So assume that you have 3 views of an object. So you're going to treat the 2 views as your source views and the 3rd view as your target view. And given a shape estimate that, of course, initially is going to be extremely accurate, you try to take this shape estimate, you try to warp it under the cameras of the source views, in order to extract the texture from them and the shape information. And when rendering that particular shape on the 3rd view, you want it to be able to match what the ground truth target view looks like. So ALAS compares these 2 views, the rendered and the target, and then through back propagation and differentiable rendering, everything can go back to the shape of that estimate, the estimate that you have, in order to update it so that it becomes more and more accurate. I'm giving a very brief description here because I'm really short on time, but I'm happy to answer any questions if there are any. And so that allows us to do things like what I'm showing here, where you have your input views of like objects. Some of them are quite complex and allows you to get the shape of the objects and the texture. Even more here, we also try to experiment with marketplace images. Actually, I think that these are from Amazon, where we take like images, like, if you want to sell a product and you place these images on eBay or Amazon or Facebook Marketplace, wherever you prefer, and then we try to extract the shapes exactly using that technique. And the only thing I wanted to say here, which is something that I found really interesting, is that this is exactly where texture is quite important. And we know this, we humans know this, but it's nice to see this also being the case for deep nets, where in order to capture concavities in shape, this can only be done by matching texture and not just silhouettes. And we're showing here exactly the effect of our model if it trained using comparing textured images versus, which is in this row, versus silhouette images, so without any texture. And as you can see, when you don't have any texture, it's quite impossible to capture any concavities, creases in the object shape. Okay, I had this one other project, and I think maybe I'll spend 2 more minutes try to present it, because I'm a big fan of this project, because it goes a little bit away from this, obsession with recognition and understanding objects and humans and everything. And it's a more graphicsy task, though it does require understanding of scenes. And it's a task of novel view synthesis, where you have an input image. This is the image that your model sees, and its goal is to predict images of that same scene, but from different viewpoints. So I said that it's a more graphicsy task. I think people love this task, but it does have a notion of understanding, because in order to predict scenes from different viewpoints, you need to understand exactly what you're seeing, what objects you're seeing. Some objects go unincluded once you move the camera around. So there is an implicit understanding that needs to happen. And so this task, we wanted to also work on this, and with the idea of using the idea of differentiable rendering. And there's a lot of previous work that I will not cover, but this slide is up there. But our approach is actually very simple. So we want to take an input image. This is the image that the network sees of the scene. And we're going to have a deep network, which will extract features for every point of for every pixel of the input image. And a depth network, this is going back to what someone said about predicting depth. So this depth network will now place all of these pixels along with their features extract from the feature network, but we'll place them in the 3D scene based on the depth prediction. So now we have a 3D point cloud. So point cloud on 3D space, where every point is associated with a feature network extracted, with a feature vector extracted from the feature network. And so under a new camera viewpoint, we're gonna render these point clouds, these latent point clouds on the new view, which will lead to this image, but an image of features from that viewpoint. So from this, these projected image features will then go through a generator. It's a network in order that transform features into RGB pixels. And of course, we're going to use a discriminator to force the images to look realistic. And we're going to compare this predicted image to the target image on the target viewpoint with a loss. And so this network does not use any 3D annotations for supervision. It only uses an image, a camera transform, and a target image. And through these all differentiable operators, we're able to learn exactly how to change the viewpoints of scenes merely from one single image viewpoint at test time. And these are scenes that our network have never seen before. So these are novel scenes at test time. Oh, yes. And the other interesting thing I wanted to say is that even though we don't have any 3D information, when we are learning these, training this network, we are able to capture via these 2D projection losses some sort of 3D structure of the scene. And so over here, we're visualizing that 3D point cloud, the latent point cloud, that is our representation when we are tackling this problem. And you see that, of course, it's not perfect, but it's definitely able to understand exactly what is near and what is far from that particular image input. And a few more point clouds, and I know I'm out of time.
So Georgia, the regions that were occluded in the initial view that become kind of visible just from the line of sight, is that just a sort of standard? I guess it ends up doing a sort of image completion there. Yes,
so exactly. So I didn't say this, but you were right to notice it. So here. When you're projecting this 3D point cloud into a new view, right here, so of course you're going to have holes because, as you mentioned, you're going to have from these different viewpoints, there's going to be parts of the scene that your network has never seen. And there is some completion that happens both inside the scene, but also in the boundaries. And this is the role of this generator network that will go from features that can have holes to an RGB image.
Right. Thanks.
Yeah.
Cool.
And yeah, so I think this is all I had for you today. And I just wanted to conclude and say that I visual recognition is very fun, and it's this abundance of tasks and benchmarks and challenges that make it extremely fun. And I really wanted to say that none of these problems that we have, what I present today as solved, are actually very far from solved. And what I think is exciting about the work that we get to do is that we get to open source all of these great tools and libraries that we build so that other people can work on them starting from exactly where we finished. And this is how I believe we're going to get to more exciting stuff, progress in computer vision, but also AI. Thank you, and I'm happy to take any questions.
Thank you, Georgia. One quick technical question from the chat. Is there any correction in the model? I think either the last one you showed or even back to the mesh RCNN for distortions from the camera. You know, if you're using a cheap camera with barrel distortion, a phone camera or something like that.
Yeah, we have, I mean, I'm going to just answer fairly, we kind of ignore the distortions from the camera. We always work with perspective cameras, and we kind of hope that distortions are not really going to be an issue for us, or we're hoping that the model is able to correct it inherently by learning how to go about this task purely from image features. But we're not doing anything to correct for distortions.
And then a much higher level question from the chat, which I'm going to generalize a little bit. Do these models, how do you deal with biases, either for particular people or gender? For example, you know, you showed this interaction model. Right. You know, how do you deal with biases in the training set or expected behaviors? I imagine that you could also think about biases in, you know, room scenes based on location, but that's maybe less of a social concern.
Yeah, I mean, there is social concerns and there is ethical concerns, and then there is also model performance concerns in terms of generalizing to new scenes. I think that these are things that we really need to be aware of when working with all of these models. And definitely data is one, but there is a lot more other issues that we need to be cognizant of. I'm not going to say that our models definitely do not generalize to unseen, even completely different parts of the world. Of course, if we're going to train them on Western living rooms that are nicely furnished and have all of these properties, they're going to learn to do that. And there's actually work in tandem with everything that I've presented that try to actually study exactly this problem of generalization. For example, somebody tried to take MaskCnn that was trained on COCO, which is a very large data set collected from Flickr. So images could be from all over the world. But it turns out that if you try to feed in a different scene, let's say a house in India or something that has maybe a different decoration and style, the models fall apart. The same goes for events, for activities like partying, or if there was one about recognizing, for example, what is a wedding dress, which is also another part of visual recognition, of course. And it turns out that, of course, if you only train it on white wedding dresses, it's never going to be able to generalize to any other wedding dress. So these are all concerns that we have and we're trying to deal with. And I believe that this is going to be something that we're going to have to work on constantly if we're working on anything data-driven.
Okay. Other questions from the audience?
This is Luca again. I have two more.
Yeah.
We'll ask quickly. One is that you have shown all these models that have a CNN backbone. Do you think this will be replaced by visual transformer? And the second one is, can you give us a little bit of insight on your how you organize your work, in the sense that all these challenges that you have shown are very challenging, a lot of data, probably you have to try many different architecture before you find the one that works. So there might be a lot of trick that I would be very interested in hearing a little bit about. Thank you.
Yeah. Of course. So first, regarding the CNN versus transformers, I think I do believe this will happen. I do believe transformers are going to replace our backbone CNNs very soon. there is still a lot of things to figure out there and understand these models better. But I feel that as time goes on and we work more on them, we understand them better, and we're more confident that they are potentially stronger than CNNs. So I do think it will happen. And I wanted to emphasize that a lot of these ideas will actually transfer. Like, you can replace the backbone with anything else that you might want. And only the switch from CNNs to transformers it's not exactly a plug and play, I would say, to these models, but very minimal changes in order to make them work, even with a transformer backbone. I mean, that's what I'm hoping. Of course, it might be the case that we will revolutionize the field altogether and just follow a completely different approach. That could also be possible. And so the second question about organizing time and not organizing work and how to proceed with research, I think this is a great question. And I think that this is I would say that this is very subjective. But the way that I go about this is I enjoy working on these new challenges and new problems and new aspects of visual recognition. And the first thing I always do when I always try to understand my data, try to understand my annotations. So this is the first thing I will do. And then I will constantly look at errors. Errors is something that no person will ever show you in a presentation, like how your model fails, because would rather show you how it succeeds. But looking at how it fails is what is going to take you to the final model, the idea, the architecture. How to fix these errors is usually what is the end product of what you see in a paper. So visualizing predictions is what I do all the time.